Okay, can everyone hear me out there? Okay, great. So what we'll do today is have a discussion about what's shown on the screen here. Tetrahydrocarbon chirality, isomer review, and the RS-CIP convention. So just as a reminder, your exam for Module 3 is this coming Friday. I've posted the exam already in Canvas. You won't be able to access it until Friday, however, but the directions are there, so you can check out the directions for that. But let's go ahead and get started. So I have a question I want to ask you based on what's drawn here on the document camera. So you'll probably have to pin me to your screen so that you can see what's going on. So consider the molecule bromochlorofluoromethane. Now what I want you to do on your sheet is draw, basically start drawing a methane derivative where you have two bonds as shown in the plane, a dash where one bond is going behind the plane, and a wedge where one bond is coming forward towards you. So go ahead and draw that first, just as it's shown here on the document camera. And then what I want you to do, so there's your carbon. I want you to then put in a bromine, a chlorine, a fluorine, and a hydrogen on your molecule. So if you're willing and able, maybe you can show your camera and let me see how you've put those substituents around that central carbon. Okay, so what I'll do then is I'll go ahead and I'll draw in these substituents. I'm going to use these colors, so I can't obviously use a white marker on white paper. So for the H of the methane, I'm going to use the orange. And I'm going to place that H here. For the bromine, I'm going to use blue, and I'm going to place that BR here. The chlorine, I'm going to use green. I'm going to place that here. And then for the fluorine, I'm going to use red, and I'm placing that sort of at the apex. So if you've drawn the substituents exactly how they're shown here, maybe type yes in the chat box. So Carly's saying she's drawn at the same. Aiden saying yes, but rotated. I'm not sure exactly what that means. If you've drawn it exactly like this, maybe type yes in the chat. James saying he had two substituents drawn backwards. So I think what Aiden and James are sort of alluding to, the point of this exercise, I'm going to redraw the methane. So I have a bond in the plane, I have the carbon, and I have another bond in the plane. Then I have the wedge, and then I have the dash. So what I'm going to do is I'm going to put the substituents in there again with the same colors, but now I'm going to draw them the following way. So both of these molecules are bromochlorofluoromethane. What is the relationship between these two molecules, though? They're both this name. So as we see in the chat, the relationship between them is they are mirror images. And so what that is if we had a mirror plane here, they would be mirror images of one another. So if you're having issues seeing that, take your left hand and your right hand and put your thumbs together and then your fingers. Those are mirror images. So what that means is, and hopefully these models will show up. So these two molecules, the central carbons are both sp3 hybridized. I'm showing that the H's, the hydrogens, the fluorines, the chlorines, and the bromines. See how they mirror one another? When you have mirror image isomers, or stereoisomers, they're called enantiomers, as we see in the chat. The thing about them is, now watch what I'm doing. I'm doing a single rotation. I'm taking this. I can line the hydrogens up with one another and the fluorines up with one another. But notice now the bromine and chlorine, those do not align. I can get those to line up. The bromines align, the chlorines align, but now the fluorine and hydrogens don't. So you can do any sort of rotation you want and get 2 of the 4 to line up, but the other 2 will not. If I were to take 2 substituents, if I take them off and change them, then they become the same thing. So let me show you what I mean by that. If I take this bromine and this fluorine off and I change them, I've converted it to the other enantiomer, which now everything will line up. So see how all the substituents now line up? the hydrogens, the fluorines, the chlorines, and the bromines. So when you have enantiomers, you can rotate them any way you want. Two substituents will line up, the other two will not. If you interconvert them in terms of changing two substituents, then you're making the same thing. And that will become important in a little bit when we discuss another way of viewing these. So right now we have these mirror image compounds. So what is the issue that we're trying to answer here? Both of these are bromochloromethane, but since there's two of them, how can they have the same name? So what we're going to do is learn some nomenclature rules for naming molecules that have what's called a chirality center or a stereogenic carbon, stereogenic center. So notice 1, 2, 3, 4. Each of these has 4 different substituents. So that's called a chirality center. We have bromine, chlorine, fluorine, H. Those are the 4 substituents. Mirror image isomers called enantiomers. So how do we differentiate them through the nomenclature? What we can do is use the atomic number for each. So in the black marker, I'm gonna put next to them, or maybe I'll do it here. I'll say atom, H, F, Cl, Br. Then in the second column, I'm putting the atomic number. H is atomic number 1. Fluorine is 9. Chlorine 17. Bromine's 35. These numbers are then related to a priority score. The higher the atomic number, the more priority that group gets. So what do I mean by that? This is the highest. We have 4 substituents. So this is going to be priority 1. 17 is then priority 2. 9 is priority 3. 1 is priority 4. We have 4 substituents. We've then numbered them in priority 1, 2, 3, 4. So now let's go back to this drawing here and put those numbers in. Hydrogen's priority 4. Bromine was 1. Chlorine was 2. Fluorine is 3. So the Kohn-Ingold-Prelog is a P. Kohn-Ingold-Prelog rule if you put the number 4 group, the lowest priority group, behind the plane, so it's projected away from you, and then you determine the rotation of the remaining 3. You'll give a designation of R for clockwise and S for counterclockwise rotation. So we're holding in my hand, I'm holding the lowest priority group, a hydrogen, which is orange. I'm holding that in my hand. I'm now projecting it away from you. We said bromine was 1, chlorine 2, fluorine 3. So when you look at that, what's the rotation of the 1, 2, and 3 groups? In the chat, you can put R or S. So I just autofocus. Maybe that's a little bit more in focus now. So I'm getting some R's, and so yeah, let's look at. So we have 1, 2, 3. So 1 going to 2 going to 3. That's clockwise. So this enantiomer is the R stereochemistry. So notice for this compound, we have 1 chirality center, but we have 2 stereoisomers. If this is R, what should this be then? What should the mirror image enantiomer be? It has to be S. So look, bromine 1, chlorine 2, fluorine 3. The hydrogen's the lowest priority group. It's away from you. 1, 2, 3. That's counterclockwise, so that's S. So let's make a note of that. So 1 chirality center is equal to a pair of enantiomers. 1 is R, 1 is S. So then basically, how do you use this information? You would stick it in front of the name. So we would say, you put these in parentheses, R, bromo, chloro, fluoro, methane. You would do the same thing for the S. So this is a skill that you need to be able to do. Given a chirality center, recognize that you have 1, 2, 3, 4 different substituents. Figure out if the chirality center is R or S. Be able to draw the mirror image enantiomer. If you're given a name that has a chirality center, be able to convert the name back into a structure. So we'll do some problems from the workbooks, but I want to talk about some issues of these 2 compounds. So we'll go over some more of these, but let me show you an issue that falls out of this. So we said this was the R, and that was the S enantiomers. So all we're doing now is looking at some physical properties. The molecular weight of each of these is 147.37 grams per mole. So if you take either of these and you put them into a mass spectrometer, you get the same molecular weight. The melting point of each of these is negative 115 degrees C. The boiling point of both 36 degrees C. The density, 1.953 grams per milliliter. 1.953 grams per milliliter. The carbon-13 NMR shows a single peak at 82.0 parts per million for both. The proton NMR shows a single peak at 7.20 parts per million. So for each of these, I've listed physical properties. So now my question for you to think about is, if these are separate compounds, and we've sort of already determined that through a thought experiment using the Koningald-Prelog nomenclature, they're mirror images. So in reality, if all these are the same, how do we know these two things actually exist as separate stereoisomers? So yes, the reason, or the experimental method that we would use is an instrument called polarimetry and optical activity. So as you see in the chat, these molecules will rotate plane polarized light in equal but opposite directions. The value that they do that in is called the specific rotation. So polarimetry tells us the optical activity, and that's the rotation of plane polarized light. The specific rotation, it's called specific because we're using a normalized set of conditions when we do that. So we'll talk about that if we have time today. If not, we'll talk about it on Wednesday. The main point here is, since the physical properties are the same, the only experiment we can use is polarimetry with plane polarized light. Carbon gives the same data, proton gives the same data, IR is going to be the same, mass spec is the same, melting point, boiling point, density. Polarimetry and the specific rotations will have equal but opposite signs. So any questions on this before we switch over to the workbook and start doing some problems to spot chirality centers in molecules? So this is page 105 in the first semester workbook. let's go ahead and look at these problems where it says in each of the following compounds there is one chirality center. Find it. Why don't we practice our skills? Let's start with 7.2. The first thing I want you to do for this structure, 7.2, is name it. So 3-methylhexane is showing up in the chat. Now that you've done that, which carbon is the chirality center? So we see from the chat, I'm going to, in the black marker here, I'm going to just put a dot. So where I put the dot in black marker, that's the chirality center. Now what I want you to do is, in the chat, tell me the 4 unique groups that are bonded to that chirality center. So Mac is pretty quick on the draw. He says propyl, ethyl, methyl, and hydrogen. So the hydrogen's not shown. Let me put it in. So there we go. Propyl, ethyl, methyl, H. Let's do the same activity for 7.3. Go ahead and name it first. So we have 2,3-dimethylpentane. Is the chirality center in 2,3-dimethylpentane. So C3. So I've drawn one of the enantiomers here. What is the stereochemistry of the chirality center at C3 in this enantiomer? So James asks, is it not C2 because it has 2 methyl groups attached? That is correct. If you're looking at carbon 2, you have methyl, methyl. Those are the same, and therefore that is not a chirality center. So for this enantiomer as drawn, what is the R or S designation? So Aiden and James say R. But my question to Aiden and James, so I'm looking here, I'm standing there, I look out, I see carbon, carbon, carbon. Carbon has an atomic number of 6. So if these are all the same priority, how then do we assign which one gets the highest priority? We have the hydrogen, which is in back. I've just put it in. That hydrogen's the lowest priority. So Aiden says the masses of things attached to those carbons. So that is correct, but I don't want to use the word mass. Let's use atomic number. Generally speaking, the atomic masses increase as you go in increasing atomic number, but the CIP rules use atomic number. So what Aiden is saying is that basically, since these are carbon, 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 so that's 6, 6, 6, you can't make a differentiation at that point about which one gets the highest priority. So then you have to look at the atomic numbers of what's bonded to those things. These are all hydrogens. You have 1, 2, 3 of them. They're all 1, 1, 1. You have 2 hydrogens, 1, 1, 1 carbon, 6. Here you have 2 carbons, 1 hydrogen, so you have 1, 6, 6. So since this has, I guess you could use the sum of these. This would be 8, 3, 13. So because that sum is higher, we would say this is priority 1, that's priority 2, and this is priority 3. So we're going clockwise. So this one as drawn, that's R. So in this problem, what we've seen is that when you're establishing the priority to determine R or S, you have to look at what's bonded to the groups if they all have the same. So Hannah's asking about where did I get the 1 and the 6. So those are the atomic numbers from the periodic table. Hydrogen's atomic number 1, carbon's atomic number 6. So again, to repeat, this is the chirality center and we're standing there. We put the lowest priority group, hydrogen, has atomic number 1, it's behind. So the remaining 3, we have to assign priorities 1, 2, and 3. When we go out, we have carbon, carbon, carbon. Those are all atomic number 6. So at that point, you can't make a decision about what gets the greatest priority. So you look at what's bonded to it. These are hydrogen atoms. So 1, 1, 1. This has 2 hydrogens, 1 carbon, 1, 1, 6. This has 2 carbons, 1 hydrogen, 1, 6, 6. So that's how we get the 1, 2, 3. We're going clockwise, so we can assign that as R. So this compound here, 7.4. Which carbon is the chirality center? So is this carbon a chirality center? Is this carbon a chirality center? So we found it because it says there's only one, so that's the chirality center. So I'm gonna flip the script on you a little bit here. What is the R or S designation of this chirality center? I've put the alcohol group going away from you. Aiden's quick off the bat, he says R. If you agree with that, type R. If not, type S. We'll see what sort of consensus we reach. So let me ask you guys a question. Oxygen has atomic number of 8. So 8 is greater than 6. So this gets the number 1 priority. You have carbon and carbon. That's atomic number 6. So the way you differentiate, this has more groups bonded to it. Carbon and carbon. This just has hydrogens. So this is 2, this is 3. Now I'm going to put the hydrogen in orange. The hydrogen's coming out towards you. That's priority group 4. So when we're looking at 1, 2, 3, this is going counterclockwise. But everyone's saying in the chat that it's R. So what's the issue here? How do we understand that? If we're going 1, 2, 3 counterclockwise, shouldn't this be S? James says yes, but Aiden, Mac, and Carly say R. Aiden says we're looking the wrong way down the lowest priority bond. So Aiden, what does that do then? Since we have the lowest priority bond projected towards us, how does that connect with your answer of R? Turns the molecule upside down from the orientation used to name it. Yeah, so basically, again, the CIP, Kohn-Ingold-Prelog rules, the rule is this. The lowest priority group must face away from you. So even though you correctly determine these priorities 1, 2, 3, and it is going counterclockwise, and you determine S, because this group is pointing towards you now, you have to flip it to get R as the correct answer. And that's only because that's what the rules say so. If your eyeball was on the other plane, so you're looking at it down from this plane, right? If you were looking at this molecule from behind the page, the lowest priority group would be behind you and you would get R. So the correct answer is R. So whenever the lowest priority group is towards you, whatever you initially figure out, you have to flip. Is that clear? So I want to move on to now this next one, 7.8. It says, in the following compound, find all the chirality centers, if any. So I think you have enough knowledge at this point to determine what the name of this compound is. So the first things first, what is the name of this compound? So 1,2-dibromocyclohexane. So yeah, it's a cyclohexane parent. You have two bromines. They're located at the 1 and the 2 position. So that's why you have to use the numerical prefix di. There's 2 of them. So because you're showing 2 numbers, 1 and 2, that sort of indicates that you have to have di. So my next question to you, how many chirality centers are present in that molecule? So there's 2. And what carbon atoms are they? What number carbon atoms are the chirality centers on? So carbons 1 and 2. So we saw before one chirality center equals 2 stereoisomers. So they're called enantiomers, right? R and S. So now we're saying there's 2 chirality centers. How many stereoisomers should there be with 2 chirality centers now? So Mac and James both say 4. Mac further clarifies that 4 maximum if there is no internal plane of symmetry. So that brings up another sort of rub to this whole issue of stereoisomers, as we see on the slide here. Four stereoisomers. With 2 stereoisomers, We said one was R, one was S. Now what I want you to do in the chat is indicate to me what are all the possible CIP designations for these 4 stereoisomers. Kahn, Ingold, Prelog, CIP. For the 4 stereoisomers, what are the possible CIP designations for those 4 stereoisomers? So we're just talking in general. It doesn't have to be for this specific compound yet. What are the 4 possibilities that we can have? Anyone got the, just type 1 possibility. We can work from 1 possibility to understand the other 3. So Aiden says a possibility is R, R. So one chirality center is R, the other is R. So what is the enantiomer of RR? In the chat, what is the enantiomer of that? So those are enantiomers. So now let's put in another term. We figured out two of the 4. So the relationship between this set of enantiomers is another set of enantiomers. What possibility could I put here? RS, and so its enantiomer is SR. So now what is the relationship between R and S? So again, these are enantiomers. So RR and RS are diastereomers. So what does a diastereomer mean? Diastereomer mean one of the chirality centers stays the same, one of them changes. What's the relationship between RR and SR? Should I use the red or blue pen, with red indicating enantiomers and blue indicating diastereomers? So RR and SR are what? So those are diastereomers. SS, SR, those are diastereomers. SS, RS, those are diastereomers. So what I want you to do is practice. You don't have to do it now, but when we leave the chat. Three chirality centers. How many stereoisomers? Then what are all their relationships, just like we did here? Again, as practice. Three chirality centers. What are all the CIP designations for the enantiomers and diastereomers? So think about that after the chat, but let's get back to this problem right here. So I'm going to redraw this, and I'm going to put some stereochemistry in. So for this stereoisomer here, what is the RS designation of the carbon I'm pointing at right now? The lowest priority group, which is the hydrogen, is away from you. We have bromine 1, carbon, carbon. This carbon has a bromine, so that gets higher priority, 1, 2, 3. So we're going to say that's R. What about this one now? The lowest priority group is coming towards you now. Remember that. So we have 1, 2, 3. That's counterclockwise, but the lowest priority group is pointing towards you. So instead of it being S, it's going to be R. So you've sort of done the heavy lifting so far. We said there's 2 stereoisomers, or 2 chiralities. That equals 4 stereoisomers. We've determined one of them already. So what are we trying to do now? We're trying to draw all 4. We've determined one. Now I'm going to draw the mirror image of this. So this is the mirror image. Mirror images are enantiomers, correct? So what is the stereochemistry at this position right here? It's what is the stereochemistry at this position? It's S. So see how they flip? R, there's your SS. Those are enantiomers. We just determined that. So we've determined one set of enantiomers. Now this is getting back to what Mac originally put. If there is something about a mirror plane, another set of enantiomers. So I'm going to keep this one the same. I drew a wedge. We already determined that was R. Now I'm going to draw another wedge. We know from this that this dash to be R, this is the opposite, so this has to be S, correct? And this is purely visual inspection from what we already determined. Now I'm going to draw the enantiomer of this. We do the same thing. R, this becomes S. S, this becomes R. So this gets back to what Mac was saying. Are these two things really mirror images of one another? If not, why not? So Aiden points out you can do a rotation. So if you imagine taking this molecule like this and flipping it over, you flip this over, these things are superimposable on one another. Even though we've already determined there's chirality centers present, these molecules have an internal mirror plane. So see here what I'm drawing in the dashed line? Everything above and below mirrors each other. These mirror each other. Everything else mirrors each other internally. So if a compound has chirality centers and an internal mirror plane, do you know what it's called? They're called meso. So instead of having 4 stereoisomers, we have 1, 2, and then 3. These are 1. So even though it says the maximum is 4, you can have lower than the maximum if you have an internal mirror plane. So these are enantiomers, correct? What is the relationship between these and then this compound here? So the relationship between either of these and this compound is called what? Yes, those are diastereomers. Now, as we said, enantiomers can only be distinguished through polarimetry and optical activity. Diastereomers will actually have different physical properties. They may not be wildly different, but they will be different enough that you can tell. So if you have the workbooks, why don't you go ahead and do some more of these problems in the workbooks and from the homeworks. We're about out of time for today. So keep in mind your exam for Module 3 is this Friday on Chapters 3, 4, and 5. You have the homework and Orion sets due then. If you have any questions, shoot me an email and we'll set up a Teams meeting for 30 minutes. If you do have questions from the homework, try to send a screen grab so I can better understand what the issue is. But other than that, we'll sign off now and we'll see you Wednesday for that chat session.